Hi everyone, my name is Shiwen. Today I'm going to introduce our course project for the course Systems for Machine Learning. This is a collaboration project with Louis, and our instructor is Professor Alexey Tumanov. Our course project is MODIN-XQ, Accelerate Interactive Data Analysis with Cross-Query Optimization. Pandas is a popular library in Python for exploratory data analysis. However, since Pandas only uses one CPU core, its query latency grows linearly with the dataset for most of the operators. The resulting long waiting time hurts the productivity of engineers, data engineers, and the data scientists. Libraries like cuDF, MODIN, and XQ are developed with the objective of accelerating Pandas workflows through GPU kernels, parallel execution, and lazy evaluation. However, they also suffer from issues like scalability or limited API coverage. To enable interactive data analysis on a larger scale, we propose MODIN-XQ, a Python library with a Pandas-like API, which accelerates interactive data analysis workflows with cross-query optimization, distributed execution, and the GPU kernels. Unlike eager frameworks like Pandas and MODIN, when the user runs a Jupyter cell, MODIN-XQ will not execute operations immediately. Instead, it will gradually construct a data flow graph as the intermediate representation. Only when the user requires to visualize a particular data frame, MODIN-XQ will schedule the necessary computation tasks to materialize the required object. In addition, MODIN-XQ will also employ a variety of data flow graphs optimization techniques to minimize the user waiting time. There are three major stages in MODIN-XQ's workflow: graph construction, graph optimization, and graph execution. Here is the architecture design of MODIN-XQ. The query compiler extracts the common patterns from Pandas APIs and classifies them from the perspective of distributed execution. By doing this, we reduce the number of APIs the lower layers need to implement. Each MODIN frame holds an array of data frame partitions, either virtual or materialized. Besides, this class is also responsible for metadata management. The query compiler maintains, optimizes, and schedules the data flow graph. And when the user requires to visualize a particular data frame, it extracts the necessary subgraph and schedule it on a set of reactors. Here is a list of graph optimization techniques. We have finished implementing pruning and caching, and we are currently working on the other three. Here is a simple example of graph construction and caching. As you can see here, when the user submitted this line of code, we construct the corresponding data flow graph. And with caching, because all these three data selection operations like the same column on the same data frame. So before we apply caching, there are three mask operations on the data flow graph, but after caching, there is only one mask operation node on the data flow graph. Next, let me show you a simple demo. The first is we import the libraries, and then we read a CSV file as a Pandas data frame. And the next, we load this Pandas data frame into our framework. But as you can see here, we only add some nodes on the data flow graph. We do not really load any data into GPUs. And next, we execute a line of code. As you can see here, the latency is really small because, again, we do not really run the computation. We just add some nodes on data flow graph. Here is a visualization of the current data flow graph. As you can see here is a little bit cluttered because there are like a subgraph for every partition, and currently there are 8 partitions. So there are like 50 to 60 nodes on this graph. And next, we execute another line of code. Again, as you can see here, the latency is about 50 milliseconds, we do not really run the computation. We just modify the data flow graph. And as you can see here, the data flow graph gets a little more complex. So next, we execute this line of code to pandas. We explicitly tell MODIN-XQ to materialize this variable A. And as you can see here, the latency is 20 seconds, is relatively long because we need to first load the data and then run the computation. And we also print the results. The next time we want to materialize this result, we want to visualize these results, the latency is really small. It's only 500 milliseconds because these nodes are already materialized, right? And next, let's materialize the other variable B. The latency is about 2.6 seconds. It is much smaller than the time when we materialize A, because right now the data loading nodes are already materialized. So it actually runs less computation than the first two pandas call. Thank you. Here is my very brief introduction. So if you are interested, feel free to take a look at our reports. Thank you.